Okay, I'm going to begin with Chapter 2. Chapter 2 is Energy, Energy Transfer, and General Energy Analysis. Okay, so here are the main topics. First thing we'll look at is this idea of energy and the different forms energy can be. Could be, like electrical energy, could be mechanical energy, chemical energy, are some examples. We'll also look at this idea of internal energy or energy contained within uh, some system or some object or some substance. We'll look at this idea of heat and what it is, work, looking at the first law of thermodynamics, which basically is the idea that energy can't be created or destroyed. Then we're going to look at uh, fluid flow across some boundary. So what we're going to do is we'll define, something like a system boundary or um, something that encloses our system. And one of the things we'll look at is fluid flowing across that boundary, okay, and what that happens, how that changes the energy, or at least, what happens to the energy, and, due to that flow coming in and leaving the boundary. Then we're going to look at energy conversion and the efficiencies associated with it. So when you convert energy from one form to another, you're always going to lose some energy. You can't get that 100% conversion, or not lose it, or some of it will be lost to its environment, typically in the form of heat. Then we're going to look at applications of energy conversion in the environment. Okay. First thing we'll look at is what's considered to be an adiabatic system, which means essentially that heat doesn't enter or leave the system. Okay. In this case, it gives you an example. If we say, as an example, two cases here, you have a room. Let's say it's like a perfectly insulated room, or no heat enters or leaves through the boundary, being the walls and the floor and the ceiling of the rooms. And the only energy that's coming in is electrical energy. Okay, so what's going to happen is that, in both cases, you have electrical energy converted to like mechanical energy in this case, and it circulates around the room. And you have a conversion factor, so like the motor, and there's friction heating up the wind when um, uh, the fan is spinning. And so you have some conversions where you're actually generating heat. So in both cases, in this case, you'll heat up the room. And the refrigerator is the same thing. You have like a heat exchanger or a heat pump, where heat is being extracted from the air and then used to essentially you're cooling the air by extracting heat from the air. And in this case, there's a conversion process from electrical energy to energy to essentially circulate the pump. So there's heat being generated. So in this case, also, the temperature will rise. Okay. So just a couple of examples and this concept of adiabatic and what that is, right? No heat, energy either enters or leaves the room or the boundary. In this case, it's a room. Okay. Right. Two, we're going to look at in different forms of energy. Okay. So we have, first thing we'll define something as a total energy of a system. And just in general, thermodynamics deals with that change, right? So we'll look at that. So there are different forms of energy here, and we have macroscopic forms of energy. It could be like um, kinetic energy, potential energy. Potential energy being essentially you're lifting the object up, or maybe you're storing the energy in a spring, something like that. Then you have microscopic forms of energy. In this case, something happened at the molecular level. Um, Something stripped, so maybe chemically it's stored. Could be an example of that. The next one, internal energy. So if you took all of these microscopic forms of energy, come up with an internal energy. And so just these two, potential and kinetic energy, which we should be familiar with from physics and like intro to engineering. Uh, so kinetic is motion, energy of motion essentially, and potential energy is our energy is due to elevation in the gravitational field, at least in this case. Okay. So here's our equations. All right. Sort of summarized them here for you from the author, but here's our kinetic energy. Um, this would be like a velocity squared. It's like 1/2 mv squared, which you should be familiar with. Here it is in terms of unit energy per unit mass. So really, essentially, we're just dividing out the mass. The next one is the potential energy and the potential energy for unit mass. Okay. As we get a little further on, we'll take a look at, like, here's mass flow rate. This is, from previously. What is that? And mass flow rate, essentially, if you look at this diagram, essentially what it is like, here's the velocity average. This is like volume flow rate, and here's our cross-sectional area. So if you multiply these two together, you're essentially coming up with a volume per unit time, okay, essentially. And then this is our density, right? And here's energy, right? Energy flow rate. So with the energy flow rate, it's just the mass flow rate times E, lowercase e, which is essentially just here, total energy per unit mass, okay? Now we can also represent the total energy of the system, which is just going to give us, what we're going to have is any internal energy, kinetic energy, and the potential energy, okay? So if we just substitute in with the appropriate equations for the kinetic energy and potential energy, here is our total energy of the system. We'd also rewrite that a little bit differently, and we can write it in terms of per unit mass. So we can divide out mass from each of these terms. And we do that, lowercase u is essentially the internal energy divided by the mass. Okay. Okay, just looking at internal energy in a little more detail, we have sensible energy. Okay, so this is like internal energy or kinetic energy is associated with or energy associated with the movement of molecules in the system. Then we have latent energy. Okay, this is in terms of its phase. Chemical energy, anything associated with atomic bonds in a molecule, and then nuclear energy, right? So thermal energy, we have sensible and latent, right, which makes up the total thermal energy in the system, okay? And then the internal is everything, plus chemical, plus nuclear, all right? Okay. Okay. Static and dynamic forms of energy. So looking at if we broke up the energy into two aspects, at least at the macroscopic level, looking at, and here's an example, let's say of a dam and a water wheel. The static form of energy is whatever is contained or stored in the system, okay? Now, there's microscopic energy, motion of the molecules, and then there's the macroscopic energy, if we talked about like an example like this. And then we have our dynamic forms of energy, or energy interaction. Okay, so the motion, essentially motion of the water flowing out that'll turn the wheel in this case. Okay, so if we look at both of them, we have macroscopic and the microscopic. In a system like this, our microscopic energies really are not useful because they're disorganized. They're not going off, like in this case, the energy, microscopic energies. The molecules are just bouncing off in different directions. Okay, but the macroscopic view, all of the molecules of the water, we can take that and we can use that. All right, so just static and some more terminology, static and dynamic forms of energy. All right, so this is the energy interaction. We can think about it in that form. All right, so so the dynamic forms are leaving the boundary, are going across the boundary. Okay, and we either gain energy or lose energy due to that. Right, like in this case, the energy in the water, some would be lost if some of it flowed out, right? Okay, so the only two forms of energy associated with a closed system are either heat transfer or work. Okay, so the heat transfer, we could have heat transfer. In this case, we're just, you know, marginal heat transfer, but pretty much we're doing work to in moving this wheel. Okay. Um, okay. So this is just defining the two, right? If you have a energy transfer that results in a temperature difference, you have heat transfer. Otherwise, you're doing work. Okay. And then one other point here is a closed system, right? So closed system essentially means you don't have any matter change, or you don't matter is not, you know, entering or leaving the system. Okay. So just some more terminology. Fission. This is when you're actually going through and splitting an atom. Fusion is when you're have two nuclei combined into a larger one, and this just gives you fusion was uncontrolled fusion reaction was achieved in the 1950s. Okay, so just quickly that. Okay, energy transfer by heat. Oh. Okay, so um, some more terminology. Kinetic theory treats molecules as tiny balls that are in motion, possess kinetic energy. And heat is basically this energy associated with the random motion of atoms and molecules. Okay, so that's heat, and then heat transfer, right? Three different ways we can get conduction. So they're contacted together. Um, they're in contact with each other, and energy flows essentially from the body of the higher temperature to the colder one. We can have convection, so you have some fluid um, transfers energy through some fluid. Maybe it's, you know, air blowing over the top of the surface or something. Um, so you can transfer heat like a, you know, in a room you have a fan off of a heater and blowing hot air towards you. That would be convection. And then radiation. This is through electromagnetic waves, like what we get from the sun, or some other, like an electrical heater that has some coils in it. Okay. All right. Okay. Continuing on with that. So we have heat transfer between two systems by due to a temperature difference. Okay. Uh, so here's like a, you know, a model of the system. And what we have when we have a closed system, the only way energy is going to go across the boundary is through heat or work. Okay, so we don't have any mass being transferred across the boundary when it's a closed system. Right? Okay. Oh, okay. So here's an example of, you know, you have some a soda can maybe after a long period of time. You know, you have um, there's no heat transfer because now you're in equilibrium with the rum. In this case, you know, at some point in time it was at 15 degrees, and you have some heat transfer warming up the soda, heat coming into the soda can, and then in this case it's at 5 degrees and you have it at a certain rate. So what you can notice here is that if the temperature difference is larger, you know, the rate at which heat either enters the system or leaves it is going to be greater. Okay, so it starts off like here's a lower temperature, so there's a bigger difference. Energy is coming into the system faster than it is, and as it warms up for more and more, the rate at which energy is coming into the soda can or the system decreases. Okay. Oh. And some more defined symbols and equations for us. So heat transfer per unit mass. Here's all the heat, total heat, and here's the mass, the total mass. Okay. And here's total heat transfer when you have some rate. So this could be, you know, 10 joules per second. Maybe this is 2 seconds. So your total heat transfer would have been 20 joules, right? Okay. And here it is the heat transfer if the heat transfer changes as a function of time. Okay. So in that case, you have some rate equation that's a function of time. Okay, so you have to integrate for it to determine what the total is. Okay, so here's an example. You have some heat coming in, have some mass, you have some time, and then of course, in this case, it'd be 30 over. We'd see that we have 6 kilowatts is the rate at which it's coming in. Really, it's just here's my delta T5. I have 30 kilojoules coming in for 5 seconds. It's going to be 6 kilojoules per second, essentially. Okay, and then this is just going to be that total energy divided by 2 kilograms. Okay, so energy is recognized as heat transfer only as it crosses the system boundary. Okay, so that's kind of the main point here, right? So it's transferring it as it crosses the boundary. That's where we define it. And adiabatic process, we found adiabatic process, what was defined previously, is that it doesn't exchange any heat with its boundary, with its surroundings. Sorry, no heat goes across this boundary. Okay, energy transfer by work. So the next topic I'm going to look at is energy transfer by work. Okay, just in terms of definition, what is work? Okay, it's basically energy associated with a force acting through a distance. All right. Now, one of the things, so here's a couple of things associated with work. Could be rising piston electrical wire, crossing of system boundaries, rotating shaft. Those are some examples. One of the things we need to pay attention to is the sign. Okay. If it's heat transfer to a system, work done by a system, they're positive. Okay. From heat from a system and work done on a system, then the sign is negative. Okay. So we'll need to pay attention to that when we work on our problems. Okay. We also have a unit work done per unit mass. And we'll also talk about this idea of power when we're referring to work done per unit time. Okay. So here it is when we're looking at a system, just from general, and we define it. We basically say heat in, heat out, work in, and work out. So when we write a problem or we go through and solve a problem, this is the typical terminology they use. Q is used for the heat, and W is used for work. Okay, heat versus work. Both of these are recognized as boundary as they cross the boundary. Okay, so work being done or work done on the system and heat exchanged, with the external environment potentially or going across the boundary. And there's one thing to pay attention. So they're both associated with process, not a state, and we'll see what that means. So they're both path functions. All right. So to think about that is that if it was a property, it was depending upon the state. You could think about it in terms of like, what's the change? Let's say this is volume, right? As an example, what's the change in volume? The volume is just going to be whatever it was initially. I'm sorry, what it is finally minus whatever it was initially. Okay, so the change is just dependent upon the state at those 2 points in time. When we look at something like work, what we have is to think about it in terms of the differentials. These are like the little incremental pieces of work, okay, as you go along. And if you sum all of those together, then you get a final work being done. So what you need to think about, this is dependent upon the path. This is independent of the path, okay? So if we're talking about a property, and those are some of the main points, and we'll see that as we work on some problems. Okay, electrical work. And in this case, like electrical work is just a voltage, and this is the number of coulombs that move through that potential difference. Okay. Electrical power is just the rate, a rate of of work. Um, it's just the voltage times the current, and if you sum that or you perform the integration of, if it was a constant, then it would just be V times I times delta T. But in this case, if these are functions of time, you could actually determine the total electrical work by performing the integration. Okay. Okay. And if here it is, if it's a constant, so here's like if it was just a DC circuit, this is how you would come up with the total work. It would just be V times I times delta T, whatever time. Okay, next is mechanical forms of work. And okay, so just thinking about the interaction between it's the system and the surroundings. So to have a work interaction, you have two requirements. So you have a boundary that must move. Maybe you're thinking about it in terms of like a piston, okay? And it's acting across the boundary, right? So here's if we have a constant force, it's just force times whatever distance, okay? Then we have work performed. Of course, if it's not constant, then we have to perform the integration, right? So we integrate essentially the force that's a function of time over some distance. Okay, there we go. So here's an example just of a visual of this work being done, and then here's a nice one, no work being done, right? Another one is shaft work. Okay, uh, it's just a force through a moment arm generates a torque. Okay, and here's the relationship between a torque is just force times whatever distance from some center point. And here's to show you what it would look like, right? So this is the radius, and then the torque or the force acting at that point. Okay. Now, the work actually being done, we can actually look at it in terms of its force times distance, as before. And how we would represent distance? Well, we would think about a point being like on this outer surface of the or the point that we're actually looking at, the outer surface of the wheel, let's say in this example. And that's just going to be 2 times pi times r times the number of times this thing is rotated around, right? So if we took a point here and we were trying to figure out how far it actually moved, it would just be 2 times pi r, okay, which is circumference times the number of times it went around, okay? So we have our force. So here's our force. We substitute T over R, okay, right, just from our previous definition of torque. And then we multiply it times S. Okay, when we do that, we're going to find the R's will cancel out here, and this is our final equation for work, shaft work. Okay. And then if we do it as terms of rate, like number of revolutions per unit time, okay, and now we have power. Okay. All right. So this is just visually kind of everything that was explained here, and here's a example of that with a boat. Spring work. Okay. Here's another one to look at. Okay. So the differential, as before we were talking about work and being like the summation of all these little differentials, what we have is any differential work done by the spring is force times essentially that little incremental length change. Okay. For linear springs, and this is commonly, at least initially when you're looking at these types of problems, it's common things to deal with a linear spring, right? So basically, if it's linear, then we just say the force is this K spring constant, which is related directly to that particular spring times its distance. Okay. And one of the things to pay attention to, usually spring constants given force over distance, or in this case, for the SI units, K newtons over meters. Okay. if we go ahead and you know, perform the integration, let's say we do the integral from position 1 to position 2, which isn't shown here. But if we do the integration uh, for a linear spring, what we would find that what we're going to have is just it'll come out to be 1/2 k, you know, x2 squared minus x1 squared. Okay, and these are the initial and final displacements. So here's the equation. If you take a look at the integral and really, like I said, perform it on the force, where the force is just kx. So you substitute kx into here, do the integration with a limit starting from 1 to 2, position 1 to 2, then you're going to come up with this. Okay. This just shows you some examples in terms of elongation. And one of the things we're going to recognize is, you know, it doesn't matter if compressed or elongated, you know, if it's stretched or compressed, essentially it's the same, you know, it's the same way to go ahead and solve this, okay? So basic idea is that, you know, when you have a linear spring, you're going to find that displacement of the spring doubles when the force is double, right? So if you have a spring, you know, with stretches by 1 meter every k newtons, if you apply a force of 2 k newtons, you're going to stretch it by, you know, 2 meters, all right? Okay, so here's visually this kind of what we set up here. Okay, so we also have work done by elastic solid bars. Okay, so we're talking about like a solid bar. It's the same thing as how we're dealing with a spring. What this is our normal stress. Okay, this is just basically it's just F over A. So if you saw that, A's would cancel out here. So this gives us how much work is being done on it. So instead of, like I said, instead of the force, you're going to have the normal stress, which is just force divided by area and times the area dx. Okay, and similar kind of thing with a liquid. You have the same idea here, where this is defined as the surface tension. Okay, all right. And surface tension is just basically, you know, it's characteristic that of a liquid that is resist external force. Its surface resists external force. Okay. And last one is work done to raise or accelerate a body. Right. So work transfer is basically work transfer needed to raise bodies equal to change in potential energy of the system. Okay. So we're going to find that. You know, it's like you raise this car by a certain height. You've done a certain amount of work, which is the same thing as giving, you know, like in this case, this elevator car, an increase in potential energy. Okay. Of course, there's a little bit of energy lost during the heat to lift it, but in general, that's pretty much what's happening, right? Okay. The work transfer needed to accelerate bodies equal to change in kinetic energy of a body. Okay. So in this case, if you do work, you're going to change the kinetic energy of the body. All right. And the last part is just some non-mechanical forms of work: electrical work, magnetic work, and electrical polarization work. Okay. And that ends pretty much overview of section 2.5.